Alright, so I'm Dan, I'm also at Babylon with Niels, and I'm working in the machine learning team. And so at Babylon we're working on a lot of very difficult AI problems. Obviously we're not a big data company, so we do have some data, but it's not like we've got terabytes of labeled information. So hence this title, so how the absence of big data doesn't stop you from learning cool stuff. There is data out there in the world, and you can use something called distributed representations, which I'm going to go into, to basically solve two main challenges we have at Babylon. So our first challenge that Niels touched on was some kind of user intent understanding system. So how do you build a model that understands user intent? But then to the second point of this, which is if I have some model that understands intent, if I'm updating the model and I already medically validated it, how do I know that the model is still okay? And in fact, you didn't in the first place, but how do you know it's still as okay in the second place? If you change the model, you've got to do the whole process again. So how can we avoid not doing that? And the second challenge is, so in the AI team, we have a big data and semantics team. They maintain this thing called the knowledge base. And it's basically this graph with 500 million nodes of medical concepts that are all linked together, but they're essentially the composition of multiple medical ontologies. I'm not sure if you're familiar with different ontologies, but there is ICD-9, ICD-10, SNOMED, and all these other things. And they all talk about sometimes the same thing, because they're just about medical stuff. So it would be nice if we knew which things were actually the same in these ontologies. So how can we make structured information more useful? Challenge one. So disclaimer, this is entirely hypothetical, but if I'm building a model that understands intent, you'd say, well, why not just build a classifier, right? So you've got somebody who types in the app, when I turned my neck the other day, my ear popped and it keeps ringing. What do I do? So you have this sequence of text here, and maybe you put it through some sequence classifier, maybe like an LSTM that we heard about in the first talk, and then it comes up with some softmax representation at the end between maybe 4 triage flows. So we've got face, hand, ear, and eye. And you can see that, yeah, okay, this is about ears, so I'm going to send them down the ear class of things, and we're all happy. But 4 classes isn't very many. What if somebody types into the app, when I walk, I get a strange pain in my right toe? And it goes through the same model, this many-to-one classification system, and if we still only had the classes face, hand, ear, and eye, it's going to have to pick one of those, because that's basically a 4-dimensional distribution. So maybe it picks face, but that's wrong, and maybe that's going to be unsafe. So what you would do is you would realize that, okay, I've got loads of queries coming through my app about feet. Maybe I should add a foot class to my classifier, but in doing so, you change the model. And if you change the model, you have to then put it through this medical validation step, which can take weeks of hard work from doctors, and ideally you'd like to focus on places other than every time you wanted to change your model. So what we want is some way of updating the system that decides where you want to go without changing the model that gives you the representation of intent. So that's the first thing. And then the second thing is, so we've got this structured information, and okay, we want this basically problem called Ontology Alignment. So I have these 2 graphs, and maybe I've got loads of different nodes that are the same, and I want to match them up. Let me try and explain how this works with maybe an example from The Hobbit. So on the left we have some ontology, which is a representation of Bilbo Baggins, and in the book he finds the One Ring, and he has fur on top of his feet, and blah, 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 right? So you've got 2 ways of describing Bilbo. What you notice is that on the left-hand side, actually Bilbo is described in terms of his attributes, and then those attributes, they're something that people of a certain race tend to have in the world of Middle-earth. Whereas on the right-hand side, it just directly says Bilbo is this race. But hobbits are basically the same concepts to you and me, irrespective of whether they're described in terms of what the properties of hobbits are or not. So what we would like to do is to automate this process. And actually this turns out to be quite a hard problem, but maybe it's suitable for deep learning. So these are 2 challenges. In summary, we want some way of adding classes to the system that works out where you go, but without changing the model, ideally. And secondly, we want to match concepts across multiple ontologies. This is the world of distributed representations, or at least this is one way of solving them. You probably heard of something like word to vec, or node to vec, or product to vec, or star to vec, or anything, but anything to vec is probably a distributed representation. And what that really means is you have some function which captures the relationship between the arguments of that function. Let's imagine for a second that we know nothing about the English language, and you read the sentence, the capital of England is London, and then you also read the sentence, the capital of Paris, the capital of France is Paris. If I knew nothing about the sentence, what I would know at least is that there are many words in the sentence that are repeated between the two cases, apart from the words England, London, France, and Paris. And so you might hypothesize that maybe if I switch London and Paris and England and France, then I have some kind of also okay sentence. And so then if you've got your deep learning hat on, what you think is, so if I have some function of London and take away function of England, that represents the change in some kind of component of some high dimensional space between England and London, which may be represented by a capital component. And then you say, great, so I've got my function, and I'm going to call it f hat and parameterize it by some function zeta with some kind of universal neural approximator. Distributed representations, so word to vec is an example, and you can train it in many, many different ways. This is specifically the skipgram way. So before I arrived at Babylon, I assumed that basically distributed representations were constructed using autoencoders, which is an encoder-decoder framework that basically reconstructs the object itself. But if you have a word with no prior understanding of what language is, the word itself is just some one hot vector, where the vector has the dimension of your vocabulary. That doesn't tell you anything. Interestingly though, in the first talk, when we were talking about kind of like encoder-decoder frameworks for pictures, what you kind of realize in a funny way is that pictures themselves are already some kind of distributed representation of the type of picture that they are. So they can already have like, so if I say, I've got like a picture of a clock, I can then look at a picture of a clock. It's not some one hot representation. It's already got some kind of structure in it. Whereas when we're dealing with words, we have to start off with some one hot, it is this word, and then we have to extract this structure in the middle. In word to vec, you end up with basically saying, from this word, I want to be able to predict the entire context of the word. So the right-hand side, capital of is London. The context is the two words either side of the word. The capital of England is London. The notion behind this is essentially, if I'm able to predict the context given the word, then words that appear in similar contexts will have similar vector representations, where the n-dimensional hidden layer is the distributed representation in this case. If you switch the sentences, so I've got France capital of is Paris, then you see that as I tend the vector Paris towards London, the distributed representations of England and France actually become identical. So you can see that at least this would hold in some framework. So that's word to vec, but distributed representations can work on anything. So given that this is the TensorFlow Meetup, I thought we should do some TensorFlow. Now there is no real reason why anybody would really want to do this, but what we're going to try and do is do like int to vec. So we're going to try and construct some distributed representation for integers. And so let's imagine that we don't know anything about integers before we start this task. And then one day you find a book that contains 2 chapters. The first chapter is all about even numbers, and it's basically just some sequence of even numbers between 0 and 8 that follow each other in some random order. And then the second chapter is of odd numbers, the numbers 1 to 9, also following each other. So, standard flags, we've got some seed to make sure that work is reproducible. The chapter size, the chapters of the odd and even books. The embedding size, which is going to be 2, that's so that I can basically plot it, but you can choose any number you want, as long as it's an integer. Learning rate and epochs, because that seemed to be quick enough for a demo. So, very good. Now the next bit is we're going to just build the corpus. So we're going to basically say, here are my even numbers, here are my odd numbers, and then I'm going to basically use NumPy to construct corpuses, And I'm going to print the first 3 even numbers in the even chapter. They turn out to be 4, 8, and 4 with this seed. And then the first 3 numbers in the odd chapter. That turns out to be 9, 5, and 3. And then, as I said before we came to Babylon, I thought that autoencoders would be good construction for distributed representations. And in this example, before we get on to something a bit more advanced, we're going to realize that autoencoders are really terrible for this task. So we're going to build basically a training set where the integer has to reconstruct itself with some 2-dimensional hidden representation. So those are the first numbers that you saw above, the 484. Now the AutoX even is going to be basically the feeder when we construct the graph. Combine all the data, and now I'm going to give like a bit of a plug. So I really like TensorLayer. I don't know if anybody else has used it here, but basically TensorLayer is developed by some guys over the road at Imperial College and also Carnegie Mellon University. And it's kind of like Keras, but a bit more TensorFlowy, so I think it's really awesome. I have a link at the end of my slides so you should check it out, but I think it's really good. Anyway, we're going to combine all the data. And then I'll just take you through the model for the autoencoder. So we've got some placeholders for the inputs, AutoX, and some placeholders for the targets, AutoY. Then we have a 10-dimensional embedding layer, because secretly I know that there are 10 numbers between, 0 and 9. Then an output layer, which is 10-dimensional, because I know that there are also 10 numbers between 0 and 9. And then we're going to descent on this with sparse softmax with cross entropy, and we're going to train it using Atom because it works pretty well. Except, of course, in the case where you use an autoencoder. And let's train it. Okay, and then we can just get the embeddings from the internal layer and plot them and see what happened. So as you can see, that really sucks, right? So we have 2, 3, and 1 at the top, 5, 4, and I gave it a corpus of odd and even numbers, and it didn't tell me anything about odd and even numbers, but that's just because I told the number to reconstruct itself. So pretty much autoencoders working on things that are already one hot, it is just not going to work. But we can upgrade this and do basically the skipgram representation that we saw with word to vec. So I'll just quickly run through that. Incidentally, there is a link at the end of this to the code, so you can grab it all from GitHub and try it out. I won't take you through this in too much detail, but essentially it's building exactly the same corpus. The model itself is has a 2-dimensional feeder for the targets. The target is the number that precedes and follows the number in question, exactly like how word to vec is trained, and everything else is basically the same. Yes, right. So as you can see now, if I use something like skipgram, I can segment integers based on whether they were even or odd. So this is what I call int to vec. And then there is another example which I won't go through, but essentially the question is like, what if I then came across a corpus where I have integers that follow each other, 0, 1, 2, 3, ... 9, and then it kind of loops back around 0, 1, 2, 3, ... 9, plus some kind of integer noise. And what you end up finding is that the distributed representation itself basically has a circle which is now ordered, so you go 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. And so I thought maybe it's some kind of cool project in the future. I don't know if you've ever seen like dot books where people draw stuff. So what I thought would be really funny was like if somebody had a picture, if I could use that neural network to build a corpus that you could then train a distributed representation that would then be the picture that they put in. So maybe that's something for the future. Anyway, so this is like int to vec. This is basically how distributed representations work, and this is why autoencoders don't work for one-hot things. Back to the presentation. Did that make sense to everyone? Yeah? Cool. Right, so I've segmented integers, but like, why is that useful for medical stuff, right? Well, if we go back to our first example, we got this question of, when I turned my neck the other day, my ear popped and it keeps ringing, what can I do? So instead of now having a classifier, what you can imagine is that this is some super high dimensional embedding space of sentences, right? So there is instead of scriptgram, there is a model called skip thought, which you basically have a sequence encoder and 2 sequence decoders for basically going through a massive corpus of, say, Wikipedia, and taking the representation of the current sentence and predicting the previous and next sentences in the corpus. So if you do something like that, this f hat maps any given sentence into the embedding space, and then if I realize that loads of ear queries go into this purple spot, then I can say, hey, maybe queries that end up at that purple spot, I should send them down the ear triage. And that's really nice, because now when I get my queries about feet, I can notice that they end up somewhere in the embedding space. I don't need to change f hat, and all I can do is just add this foot class in some volume in the embedding space. And that's really important, because the only set that strictly needs revalidating is that set which would have had classes change from something before that has now become the class foot. Because everything else that lands anywhere else in the volume of the embedding space is now unchanged. Okay? So this is how we've solved our problem of, I don't need to change the model, I only need to change the system, so I only need to revalidate a subset of inputs from the model. And secondly, so this distributed representations of structured knowledge. So node2vec is like a non-deterministic representation of a node's neighborhood in a graph, but there are also things like graph variational autoencoders and various other things that basically use the node's neighborhood as its context. And what you can have is basically the 2 different ontologies can map to a distributed representation in their own internal space, and then you can use something like Niels mentioned earlier about the sentence word alignment in multiple languages, and kind of treat the 2 ontologies as different languages, and then rotate the distributed representations of the graphs into each other, and then basically go, oh, the ring of power is like near the one ring, or something. Okay, so to wrap up, I think distributed representations are really cool because you don't need loads and loads of data in order to, well, loads and loads of label data in order to build them. It's also like really cool because you end up thinking about models in really weird ways. Like you're trying to pretend that an unsupervised task is a supervised task, and you're looking for corpuses where you can build the context in a specific way that means that the distributed representation itself is actually going to be useful for the task that you're working on. So I think that's really awesome. And if you're working in an environment that needs medical validation or even like validation of any kind because you've got high regulation, this can stop your model basically needing updating and validating all the time. Right, that's it. Thanks. Any questions?
So which model do you exactly use for graph embeddings? There are several techniques for graph embeddings.
Yeah, so the question is, which model would you use for graph embeddings? So this slide, right? So I said you could use node2vec, but basically you want to have a node try and reconstruct some representation of the context of the node, which would typically be taken as the context. So you can use node2vec, that works kind of okay, though the non-deterministic nature can kind of hit you, so you'll have problems with like, you know, an ontology can't self-align, like this is a bit of a problem, but you can work to some extent. Something a bit more deterministic like graph LSTM or relational graph convolutional neural networks, they can give you good representations.